Welcome friends. We are learning about the components of digital instruments, and in this series today we are going to learn two new concepts. These are the voltage to frequency converter and the phase lock loop. So let us learn one by one how these components of the digital instruments play the role when we design a digital instrument. So we start with the voltage to frequency converter. So it is composed of the operational amplifiers and pulse generator. So the operational amplifiers are used as integrators and comparators. So let us draw the circuit connection for the voltage to frequency converter. We have an op amp which is basically integrating. So the negative input is fed back through a capacitor, and there is a resistor of value R. The negative feedback path will have a capacitor C. There are possible corrections in the textbook that you need to make. Then this output reaches a comparator. So here I have a comparator like this. So this comparator has a non-inverting input and inverting input, where the inverting input is provided with a negative reference voltage. I can write minus Eref. This output, the output frequency which we are interested in, the output frequency, this is taken and fed to a pulse generator. So basically this is a pulse generator. So it will sense the change in the comparator output, that is the polarity, and accordingly a pulse train will be triggered by the pulse generator. So this pulse generator is connected to the inverting input of the op amp of the integrator. So the non-inverting input is grounded. So the voltage input which we are going to convert is given to this point, and we are using an integrating circuit. So how the circuit works? So if you see, the input is given to the inverting input of the integrator. So this is a positive input. So gradually we will develop a positive charge on the front plate of the capacitor and the negative charge on the other plate of the capacitor. So as the positive charge keeps on growing up, the negative charge also keeps on growing up, but with the opposite polarity. So once it reaches a value, when this crosses the minus Eref point, so we can see that there will be the change of sign of the output when it crosses 0, because once both the signals, both inputs are same, so output becomes 0, and after that, because the negative going voltage is even greater in magnitude, so output will become negative, and this negative voltage will punch in a negative edge trigger in the pulse generator. This will generate a train of pulses at the output of the pulse generator. This could be a pulses of grounding signal. So this grounding signal will force the capacitor to discharge very fast, because the pulse generator will provide a low resistance path to the integrator. So the resistance R1, which is very much less, and this path will give a fast drainage of the voltage on the positive plate of the capacitor. Thus The discharging of capacitor will lead to the repeat of the charging and discharging process gradually through different cycles. So in this way, the input voltage is sensed and an equivalent frequency is developed at the output of the voltage to frequency converter. So that is how a voltage to frequency converter works, and there are different kinds of voltage to frequency converters. Even there is voltage controlled oscillator, in which a little different concept is used. We will learn it a little later in phase lock loop concept. So we can understand that a voltage to frequency converter is used to convert a given voltage into an equivalent frequency, which is used in the instrumentation of digital components or digital instruments. So the next topic we are going to see is the phase lock loop. So a phase lock loop is basically converting an input DC voltage into an equivalent output frequency, or you can say an output phase, because if you obtain a frequency, it can be easily converted into phase by using the formula theta equals to omega t. So in phase lock loop, we have a comparator. So this comparator will compare two inputs, that is the DC input, which is the V in. This is the input DC voltage. This is the input DC voltage, and this is compared with another voltage that we are going to discuss, another voltage, and this voltage will produce a compared output, which will trigger a voltage controlled oscillator. So it will go to a voltage controlled oscillator, voltage controlled oscillator. So we can say this is VCO. So the output of the VCO is an equivalent phase or frequency that is of our interest. So this is the output of the VCO, which is producing a proportional phase as compared to the DC input voltage. So in this arrangement, we require a special component which is called the phase detector circuit. So we have a phase detector circuit, a phase detector circuit. So this phase detector circuit will basically take the phase of the voltage controlled oscillator, and this will compare the corresponding voltage with the input voltage. So how it works? The VCO is basically, it is converting the voltage into frequency. So a VCO is a high frequency oscillator of LC circuit. So it has many capacitors in combination with inductor or inductors to produce a high frequency oscillatory circuit. So here one of the capacitors of the VCO is replaced by a varactor diode. So how the varactor diode plays the role here? The varactor diode is used in the reversed bias mode when the capacitance of the varactor diode changes in proportion to the applied reverse bias voltage. So if the voltage applied to a LC oscillator changes, due to the presence of the varactor diode, the frequency generated by the AC oscillator is changing. So whenever I am changing the voltage applied to the AC oscillator, then the AC oscillator will produce a corresponding frequency which will be different in proportion to the applied voltage to the LC oscillator. Now, the phase detector circuit, what is its role? It detects the phase of the voltage controlled oscillator circuit, because the frequency output of the voltage controlled oscillator circuit can be equivalently converted into the phase, and this phase is sensed by the phase detector circuit. The phase detector circuit, as you can see here, it will convert the phase of the voltage controlled oscillator into an equivalent voltage. This equivalent voltage is compared with the input, which is a DC. So this input is compared with the output of the phase detector circuit, and thus the comparator will produce a difference in the voltage, and that difference in the voltage will again change the frequency of the AC oscillator within the voltage controlled oscillator. So hence the phase of the output of the voltage controlled oscillator is in proportion to the voltage input, and thus we can say that the phase of the VCO is logged along with the input voltage. So we can say that the VCO output frequency change is a replica of the change in the input voltage Vin. The phase lock loop circuit can be used as a log-in amplifier, voltage to frequency converter for a very small amplitude of voltage. It can be as small as the nanovolt range, because the input voltages could be very small in magnitude. We require to use such circuits in the sophisticated digital instrumentation. And another application of phase lock loop is the frequency modulation and demodulation. So with this, our study on the components of digital instruments is completed. So let us recap on what are the important features of the basic components. So we have a recap on all the topics we studied so far. We start with the crystal oscilloscope. Crystal oscilloscope. So we have seen that in case of crystal oscilloscope, for generating the high frequency, there are other options like inductor capacitor oscillators, which have the limitation of the low temperature stability, and its operation is limited to temperature variations also. So for digital systems, we prefer to use the piezoelectric crystals, where the crystal clocks of frequency 1 MHz or higher are used with different frequency division schemes. The next topic we studied was the counters, and the example which we had taken was a decade counter. A decade counter. So a decade counter can be formed using different flip-flops like D-type flip-flop, toggle-type flip-flop, JK flip-flop, and SR flip-flop, edge-triggered also. So in our example, we studied about the edge-triggered SR flip-flop, where we developed a decade counter using 4 flip-flops because we need to have a count between 0 to 10. So we have understood that we need to have special circuit to develop the decade counter using SR flip-flop, where the last bit has to be reset using different element of AND gate. So our next topic was the converters. So we studied basically two types of converters which are popularly used. First one was dual slope converter, and the second one was successive approximation converter. So as the name suggests, in case of dual slope converter, we have dual slope of charging and discharging. So here we use the op amps as integrator and comparator, while 16-bit binary counter is used for counting and displaying purpose. So in case of dual slope converter, we have a charging process according to the input voltage to be charged, and once the charging is done for a given voltage in a given fixed time for whatever be the voltage. So according to the magnitude of the voltage, the integrator will charge the capacitor. So once the charging is completed, the counter is reset from FFFF to 0000, and the discharging starts according to the voltage stored on the capacitor. So more is the input voltage, more will be the discharge time for the capacitor, and this will basically determine how much will be the final count for the 16-bit binary counter. So here we understand that the time taken for the completion of the conversion process is not fixed but variable depending upon the voltage to be measured and converted. So to overcome this issue, we had studied about the successive approximation converter. So here we had a special mechanism of serial address register and ring counter, where the voltage to be converted from analog to digital is sensed by the comparator, and an error voltage reaches the SAR or serial address register. The serial address register will have, in case of 8-bit register, this register will set or reset all the 8 bits starting from MSB. So whenever the comparison will produce a result which is greater or lesser than the corresponding bit voltage, it will either set or reset the bit for the register. So we have studied by taking the example of a 0 volt to 10 volt range of serial address register, where we tried to measure 7 volt and convert it into DC. So as we can recall that the first half of the voltage, that is 5 volt, will set the MSB, while the second half of the voltage, that is 2.5 volt, will not set the register because the remaining voltage from 7 volt will be 7 minus 5 equal to 2. So this second bit after MSB will be reset to 0. Similarly, all the 8 bits are set or reset, and thus this process of conversion has a fixed time of conversion. So this time will be comparatively less than the earlier case, because in case of dual slope approximation we have charging and discharging time of the capacitor of the integrator, while in case of successive approximation there is no such situation of charging or discharging of capacitor. So definitely successive approximation technique is the faster technique. Then the next topic we studied in this session is voltage to frequency conversion. So in voltage to frequency conversion, we have seen that we are using 2 op amps and a pulse generator. So this first op amp is used as an integrator, and I suggested about be careful about the sign of the input, because the terminal which is used for integrating is a negative feedback terminal. So accordingly circuit connection has to be made, and the output of the integrator goes to a comparator which compares with it with a negative reference voltage, and as soon as the output of the integrator goes below this negative reference voltage while charging the plates, it will generate a negative pulse which will trigger the pulse generator, and this pulse generator will trigger a train of pulses, would be possibly the grounding pulse, which will discharge the capacitor fast, and this process of charging and discharging will repeat to keep a frequency at the output of the comparator which is basically proportional to the input voltage to the integrator. So in this way the input voltage to the integrator is converted into an equivalent output of frequency. The other topic we discussed is the phase lock loop. Phase lock loop, which is using a special voltage controlled oscillator which is made of capacitors, inductors and a varactor. So here the input voltage is of DC type, which has to be compared using a comparator, and the output of the comparator goes to the voltage controlled oscillator, and thus the phase or frequency of the oscillator is sensed by the phase detector circuit, and this circuit will generate an equivalent voltage which is comparing with the DC input voltage. Thus the comparison of the phase detector output and the input DC voltage will generate an error signal that will gradually change the output phase of the voltage controlled oscillator. So eventually when there is no error at the output of the comparator, the phase of the voltage controlled oscillator output is locked, and this locking is corresponding to the input DC voltage. So that is why we call it as phase locked loop. So friends, to anticipate our understanding and apply on practical situation, let us have some quiz. So the first question of the quiz is quiz 1. We use we use the following A to D converter, A to D converter in fixed conversion time in digital instrumentation. The first option is PLL, phase lock loop. The second option is voltage to frequency converter. The third option is the dual slope converter, and the fourth option is the successive approximation converter. So take a pause and have a thought the topics you studied, and then come back to tick the correct answer. So friends, as we learned that the analog to digital converters are of two types in our scope, that is the dual slope converter and the successive approximation converter. And again I am emphasizing that the dual slope converter has a variable conversion time, and this conversion time is large, and a more specific and time bound converter for analog to digital signal conversion is the successive approximation converter, which converts the input analog signal in a fixed period of time because of the method used. So that is why the correct answer is the fourth one. Let us go to the next quiz. We have quiz 2. So we use op amp integrators in one or more of the following. So the first option is dual slope converter. The second option is successive approximation converter. The third option is voltage to frequency converter, and the fourth option is phase lock loop. So again you can take a pause and think back, and you have a thought about the circuit used in different applications, which are the most important from understanding point of view and also for examination point of view. So if we think of the circuit, we find that dual slope converter uses an integrating circuit with op amp. So the first one we put the tick, then the successive approximation converter, where we have the op amp but not as an integrator but as a comparator, so this we reject. Next one is voltage to frequency converter. So here we have op amp for comparison as well as integrating purpose, so we tick over here. And the fourth one is phase lock loop, where we are using op amp of course but not as an integrator, only as a comparator, so this is the wrong answer. So we have dual slope converter and voltage to frequency converter as the correct answer. Let us go to the next quiz. Quiz 3. So if you are using the serial address register, serial address register of 8 bit to use in successive approximation converter to convert a voltage that is analog of value 7.7 into digital bits, obtain the register value after conversion. So here we are assuming that the voltage range of the analog input is kept from 0 volt to 10 volt. So the options are like this: 0 1 0 1 0 1 0 1. Second option is 1 1 0 0 0 1 1 0. Third option is 1 1 0 0 0 1 0 1, and the fourth option is 0 1 0 0 0 1 0 1. So you take a pause and solve it by the method taught to you, then you attempt the answer. So let us see how this problem can be solved. So we have the 8-bit register. Let us design a 8-bit register. 1 2 3 4 5 6 7 and 8. So this is the MSB. So you can say that you can write this is B7, B6, B5, B4, B3, B2, B1 and B0. So the 0 to 10 volt can be divided. The MSB will have the equivalent of 5 volt, then 2.5 volt, then 1.25, then it comes 0.625, then it comes 0.3125, this is 3125, then you have 0.15625, then you have 0.078125, then you have 0.039065. So these are actually the voltage divided by 2. So 5 divided by 2 is 2.5, divided by 2 is 1.25, like that we go. So we start setting from the left. So we have the 7.7 volt in hand. So once we start, we assign the 5 volt over here. This is set to 1. We are remaining with 2.7. Then the next one is 2.5. So we assign 1 bit. So remaining is 0.2. So next one is 1.25, which is more. So we keep it 0. So remaining is 2.0.2. Next is 0. This is 0.625. So I write it clearly, 0.625. So here I have 0.2. So this is 0 and I keep 0.2. Then 0.3125, again 0, remaining is 0.2. Then 0.15625. So I can assign 1 and remaining is 0.4375, and next is less than this, so assign 0, and this is 0.4375. This is actually 0.04375. So here again this is 0.04375, and next is 0.039065, which is less, so we assign 1 and the remainder will be here. So that will be the error in the measurement because all the values could not be assigned. So that is how we got the answer 11000101. So the answer 11000101 is the third option. So this is the right answer for you. So through this we have a recapitulation of the components of the digital instrumentation, and friends, in the next session we will see how different types of digital voltmeters are designed and their functioning. So this is the textbook by Professor A.K. Sawane. You can refer to it. There are a lot of objective questions as well as exercises behind the book. You can practice it. So friends, if the lecture was useful, please like the video and subscribe it if still you have not subscribed, and set the bell icon for notifications. You can send me queries at emmifaq@gmail.com, and my students can send me one WhatsApp message and phone call also. Thank you for your patient listening.